Hello, my name is Rob Trace, and I'll be here talking to you today about the new HTTP2 protocol and how it's implemented in Windows 10. So, what we're going to talk about, first, just a real brief summary of why HTTP2 is important, why we've spent the time and effort to implement it in Windows 10. Then we will talk about an overview of HTTP2, how it works, how it's different from HTTP 1.1. And then lastly, what it means to be in Windows 10 and how it actually shows up for developers and for our customers. So why did we go to all this effort to define a new internet standard? A few years ago, there was a huge realization that performance matters. A lot of studies were done by sites like Google, by Microsoft, by Amazon, about the effects of slow site performance, about slow app performance on user behavior. And what we found was that money is defined a lot by site performance. Slow sites, users click away, they go use somebody else's site. So through that investigation, there was also a realization that HTTP 1.1 was holding back site performance. The way that HTTP 1.1 transfers data across the internet causes inherent slowness, is affected very heavily by latency, and was a problem for basically taking site performance to where it is, where we wanted to get it to. It's also a very large problem for mobile networks, and as they started to emerge, we saw more and more high latency networks, more and more users using these latency networks, and more site slowness. In addition to that, over the last 3 years or so, there's been a very large movement towards using TLS by default. Microsoft themselves has announced that they're going to be moving all of their sites over to TLS. You'll see moves by similar companies throughout the industry. And when we migrate to TLS, TLS also is impacted by the latency problem and makes the problem with HTTP 1.1 connections even greater. Lastly, the web is evolving, and there's a need for more bidirectional communications. There's a need for cheaper, quicker, faster protocols for us to enable new site development, new application development. This is really what was behind the motivation for starting on a protocol HTTP2. So when you look at the draft for HTTP2, you'll see a section on what was the motivating factors, what were the requirements that we were trying to achieve with a new protocol. And the number one thing was to make a user-perceivable difference in site performance. And what we want to be able to see is users have the feeling that their apps and their sites are actually performing faster. The second thing is that it's impossible to develop a new protocol if it doesn't work over the existing infrastructure. So a primary goal of HTTP2 was to be able to traverse the existing internet and all of the things that are out there, whether it's proxies, whether it's ISPs, gateways, all of these different technologies that are deployed today. Any new protocol has to work over this infrastructure. And then the last thing was, it was a real definable goal to work with today's content. We wanted to be able to have a protocol that worked with the applications, with the sites, with the content as it was developed today. It does not mean that content won't evolve in the future to be better with HTTP2. But it does mean that we wanted to take an existing site, run it with a new transport, and then be able to see the user benefits out of it right away. It gave us something that we could use immediately that would then evolve application and site development for the long term. So what is HTTP2 essentially? Primarily, HTTP2 is a different mapping of the HTTP transport and the HTTP semantics to TCP. And what it enables is multiplexing at its heart. This gives us the ability to send and receive data, multiple requests, receive multiple responses over the same TCP channel. In addition to that, we've included header compression in the protocol, which is going to mean that less bytes are sent over the wire. Very important for scenarios like mobile broadband, or where we have costed links or slow links. And the last one is server push. And server push enables a server side, to anticipate requests and to send the content and pre-prime the client for the requests that are going to be coming throughout the application. These three features are really the heart of what HTTP2 is going to be. So HTTP2 is a negotiated protocol, and this is one of the reasons that it is compatible with the web as deployed today. It works over the standard HTTP ports, port 80 and port 443, and it works with the schemes that are existing today in HTTP and HTTPS. It is exactly the same as HTTP 1.1 and 1.0 before it. So when my application requests a resource over HTTPS, by default we will use port 443. If I use HTTP, it will stay on port 80. In addition to this, it also will support a URI that has a custom port like 8080. So it works in the same way as HTTP 1.1, and therefore it'll work with the same content and retain the same semantics. The second thing is just really important, wanted to highlight that HTTP2, the specification, works with both HTTP scheme and HTTPS scheme, meaning that it is possible to send HTTP2 across the internet in clear text. How this works and how this is negotiated is when I use an HTTPS URI, we'll negotiate TCP connection first, and then we'll negotiate TLS. It's exactly the same process as you get when you use HTTP 1.1. But when the client sends the TLS client hello, we include an ALPN extension that will have a protocol identifier of H2. And H2 essentially is the client's advertisement that it is possible to talk to me over HTTP2. The server takes the client hello, looks at that, and if it supports HTTP2 as well, it will return the server hello with the ALPN identifier of H2. And at this point, both sides have accepted that they support H2, and will start with a settings frame in HTTP2 the minute the TLS completes. With this negotiation, this means that a site running an older web server that only supports HTTP 1.1 will see this TLS negotiation, will not reply with H2, and the client will continue normally on HTTP 1.1. But a site that is an upgraded server will then see the H2 marker, will then respond with its own extension and protocol string, and the connection will proceed over HTTP2. It's very simple. For clear text, it's similar. We start with a TCP negotiation and we set up the connection. And then we send our first request over HTTP 1.1. And that request is allowed to include an upgrade header that indicates the client is available over HTTP2. When the server sees that upgrade header, the server then can send back a response saying that, great, we'll send back a switching protocol responses. And then every subsequent request on that connection will be over HTTP2.0. Essentially, the client on their next packet will send out the settings frame. So what this enables is that both HTTPS and HTTP transports can be negotiated and can be supported essentially in an environment where the client can support HTTP 1.1 and HTTP2 and can connect to any server regardless of what they support. Now, for Windows 10, we are not going to be supporting the HTTP scheme and the clear text initially. This is something that we anticipate will evolve and we will implement over the long term, but it is not going to be in the first release of Windows 10. So connections. This is really, again, at the heart of the protocol is after we've decided between the client and server that we're going to use HTTP2, we're going to set up connections, and there's a new concept in HTTP2 called a stream. Now, a stream is essentially a request-response pair, but we manage multiple streams within one connection. So with HTTP 1.1, how this worked was the client sets up a connection and goes ahead and makes their first request. That request has to fully complete before they can make their second connection, their second request, and so on for the third and the fourth. Now, what clients do in HTTP 1.1 to overcome this head of line blocking is that they'll set up multiple connections. So when I have one connection that has a request in flight, and I have a second request that I need to make, I'll open a second connection, and then a third, and then a fourth. What this does is we'll see a lot of TCP connections coming out of the client, and they're all subject to a slow start. They're all subject to latency of setting up the connection, and in particular with TLS, we'll have latency of setting up the TLS portion of the connection. With HTTP2, it's very different. We set up one connection, and so we pay the cost of setting up the connection only once. And then once we've set up that connection, we can initiate multiple streams, and these streams can be delivered out of order, and they can be requested up to 100 at a time. The protocol actually will allow for more, but the 100 is the default. So what will happen now with the client, as we queue up requests, we can put those on the wire and send them off to the server right away. And then the server can respond back in the order that the server thinks it makes the most sense. Meaning that if I have content that is ready to be sent right away and I have an idle TCP connection, I can start sending that data to the client right now, while I may be off calculating a different response. So what happens is now we can fully optimize the transport between the client and the server, depending on what's most important or the things that are queued up or that the client requests. The other piece of the protocol that comes in here is that the client can advertise a priority, which means that the client can tell the server what is the most important thing to deliver back to it. So now the server has context about what the client wants and can again make these decisions on how to best send it back to the client. And the streams, very simple. There are streams that are initiated by the client, and then there are push streams, which we'll cover in just a second, that are initiated by the server. The client streams are always an odd number stream. The server streams are always an even number stream. So the stream lifecycle is also an important concept. And it really starts with when a client wants to go ahead and request a resource. So the client opens their connection and they want to create a stream. And so what that does is that puts the stream into the open state. When the client decides it's going to send a resource, it opens a stream essentially, and then goes ahead and sends out its header frame. This creates an open stream from both standpoints, the client and the server. That stream then continues as long as the client is continuing to, say, transmit data. When the client is done transmitting its headers field, or if it is has data associated with the request, is done transmitting data, it sends an end stream message, and it adds an end stream flag. And so once the client sends an end stream flag, that stream is closed from the client's perspective, meaning that it has sent all the data it's going to send, and the server should know that. And when it does, that makes the session half closed local. The server has the same process. As the server sends back headers and data, when it is done, it can send back an end stream flag. And so again, that end stream flag, when it is received by the client, becomes half closed remote. And then the stream transitions into a closed state when both sides have sent an end stream and it closes. The other way that a stream can transition directly from open to closed is that a client or a server can send a reset stream message. And when we send a reset stream, that means that stream must be torn down and all state and all processing on it needs to cease. So a stream can transition directly from open to closed. The other state that we'll have is the idle state. And the idle state is when we're using server push, meaning that the server is intending to push resources to the client. And how that works is the server initially sends a message called a push promise. And that push promise indicates all of the resources that the server wants to push to the client. Each one of those resources creates a stream on the client that is in an idle state. And the client is waiting for more data from the server at that point. Now, what happens is that the push promise opens the stream into idle. As the server sends data, or the client can send things like a reset stream message, that the stream will move from an idle state to an open state. Those streams are then reserved when the server has sent those push promise messages. And as data transmits, it goes from open, and then we go into the end stream flags where we end up in the half closed states, or we end up in a closed state when both sides are done transmitting on that particular stream. And then we clean up after that. So what this is there's a simple life cycle to every stream, and it really extends to the extent of a send, request, and then the response. And once data is all done, both sides can indicate that we're done, and we can clean up the stream. We can clean up the stream without closing the connection. And we definitely want to keep the connection open until all of the streams, all of the requests and responses have come in. A little bit different model than with HTTP 1.1. The next feature that is in HTTP 2 is header compression. And header compression is essentially taking a header and we're going to start replacing it with literal values. And what we do is we generate two tables. There's a built-in static table of a certain limited number of headers that are pre-indexed in the system. And those headers might include method get, they might include scheme as HTTP, and what they are is they're indexed into a table that is essentially at the start of every connection. There's a second table that is a dynamic table, and that is as the lifetime of a connection progresses, we can add entries into the compression table that are going to be reused. For example, a cookie or maybe the user agent string. And how this progresses is that the client, as they send headers, can then indicate whether this is an indexed reference to an item that already exists in the table, or whether it's a literal value that may potentially be indexed into the table. The static table never changes, but the dynamic table is a running list of how what the current state of the connection is. The list is ordered, meaning that the first entry goes in is the first entry goes out. It is also limited in size. So the size of the table is defined by the connection setup that goes on between the client and the server. What will happen is that as we add new items to the table, and if the table exceeds the maximum size, we will then take out the entries that came in first. So it's basically a rolling list, and it is ordered. It is also possible to have multiple entries of the exact same header in the dynamic table, meaning that I could put user agent or some other header into the table multiple times. And that multiple times can be with the same value or with different values, meaning I could put multiple cookies into the table at the same time. So the operation itself, there are basically two types of headers now. There is an indexed header, which means that I've referenced the header by supplying its index name. And what happens is on the encoder side, when we're sending data, we can look for the header in the table, and we can replace the full header with just its index. And then when we transmit that to the other side of the connection, the decoder will find that index and will replace it with what the value is in the table. This is the heart of the compression. This is how we reduce the number of bytes we're actually sent on the wire. The other way is that we send a literal, which is the full header. And then that literal can be marked in three ways. Number one is add this to the table. So we add it to the dynamic table. So if we have a new header that we want to add to the table, we can just mark it as add this to the table. If we want to have an item that we should not add to the table, we can mark it as do not add to the table. And then the third state is never add this to the table. And that's really an instruction for all of the intermediaries between the client and the server to not add this to their table all the way through and leave it as a literal throughout the connection end to end. What this does is by having this mechanism where we indicate from the sender what to add and what not to add to the table, we can have a matching table between the client and the sender for both the send and receive paths. So as a client, I will end up with a send table where I add values depending on what I want to have into the table and marking them as a literal that say add to the table. The server, as the receiver, will then respect those markings on the literal messages and create an identical table on the server side. That process works in reverse as well. So when the server is the sender and transmitting a response, there is a separate table that is maintained for this flow. And the server then controls what gets added to that table, and the client receives those literals and respects it and builds an identical table. This scheme came out of the fact that in previous iterations of protocols, they were using a more standard compression scheme like gzip, but this was found to be vulnerable to a crime attack. And the value of the HPAC is that it's an efficient protocol. It's a way to get a high rate of compression, but without the vulnerabilities that were in the gzip solutions previously. So the third major feature here with HTTP2 is server push. And what server push does is it allows the server to anticipate what the client is going to ask for and send them to the client to pre-warm the cache. This is really useful in this case where I have a lot of static resources that are part of building a page, where I can start sending those back to the client before the client even asks for them. So while I have space in my connection, I can send back resources that I already know the client is going to ask for based on whatever his first request was. And how this works is the client always starts every connection with a settings frame, and then they make a get inside of a stream. Every server push has to be anchored to a open stream. You can't start pushing unless the client has actually made a request. So once the client makes a request, the server application can then determine that, hey, this client is going to make a bunch of other requests, and I want to go ahead and send him the resources now to make sure that he's going to get them as fast as possible. So the server application can call APIs within Windows from IIS and from ASP.NET that says, please push these resources. What this does inside of the Windows system is it creates an artificial get, and we push that get back up to the application, and it sees it just like a client had asked for. And from there, that will create within the stack a push promise. And a push promise is a list of all of the resources that we intend to push. We're advertising to the client, here's a list of things that we want to push to you. This is the list that the server application generated and called into ASP.NET. So we send this message across with a list of all the resources we intend to push. And then we can begin pushing on those streams. Each one of those push promises creates a stream in an idle state. And then when we start to push on them, we actually move it into an open state. This was from the stream lifecycle a couple of slides ago. As we're pushing these things, then the server can also respond to the initial get in the same time. The main thing is that the server cannot close the stream, cannot send an end stream, until it is done with all the pushes that are anchored to that first stream. So it will have to, that first get, that first stream, has to remain open while all the other pushes complete. On the client side with the server push, what happens is the client collects all of the pushes in an in-memory cache. They don't push directly into the HTTP cache. And then as we hit the resources we need to acquire, in the other code that is sent, say that there are links in the index.html or ASPX, those things are requested. They're pulled out of the in-memory cache without hitting the wire. They're served back to the client application very quickly. And then we go through a normal cache processing where we can add it to the HTTP cache, and we can validate the resources and all those things just as if we were in a normal operation. We just eliminate the network latency time. So how is HTTP2 going to affect web applications? There are a few ways that we anticipate. The first thing is that when we start to open hanging gets, they don't block connections. So we have one connection now. We can use it for as many resources as we'd like to. We have this huge number of streams we can open up. We can now send out a get that we don't expect to be fulfilled for some time, and it doesn't block the TCP connection. Now we can do other things on that same connection without having to have something just open and waiting for the request to be filled. The second thing is that today, to increase parallelism, a lot of sites have sharded their content. They've created multiple domains so that a client will create many open connections and we can have lots of requests in parallel. This is no longer necessary with HTTP2. So where resources are held on the same server, they can now be put into the same domain, and then we will get better connection reuse. We won't be flooding the servers, say, with TCP and TLS connections. We have server push, and there's going to be lots of different uses for server push. The most basic example is obviously a website that knows it wants to push resources based on the first GET. There will be other uses, and we anticipate that people will come up with lots of creative ways to help their clients make their applications more efficient and faster by using server push. There is an opportunity now to use smaller bits of content. No longer does a request and response block a TCP connection where latency will cause us to not send as much data. We can take content and break it up into smaller chunks that may be more cacheable than having one large, say, inline chunk. And by doing that, what you're going to do is you're going to enable clients to cache resources, even proxies or intermediaries to cache resources more efficiently than they do necessarily today. And therefore, we'll end up with, over the long term, less data sent. So this is an opportunity for us to better use the web as it was defined. And then lastly, you're going to have fewer connections, but they'll be longer lived. This means a lot less connection setup time. This means a lot less state for maintaining a number of connections. It means a better use of the network as a whole underneath us. It's a better model for using the actual TCP/IP protocol. So in Windows 10, how does HTTP2 show up? With the original goal that HTTP2 was useful with existing content, with existing applications, and over the existing web, it was possible to implement HTTP2 in a very transparent way to the application ecosystem. So we have implemented HTTP2 in the WinINet client stack and the HTTP server stack. And in this way that HTTP2 is handled completely by Windows and the operating system itself. And then over the top of that, we have a number of application platforms. And all of these get HTTP2 support automatically. Spartan, for example, will have HTTP2 support on by default automatically. So when we hit a server that supports HTTP2, this will get negotiated, and then the connection will continue as HTTP2 when both the server and the client support it. The same thing for IE, WWA, WebView, WebOC. One of the exceptions in here is the WebOC platform. And here, because of some of our legacy applications, we have HTTP2 off by default, and it can be enabled by a registry key so that we can take advantage of it if it's appropriate for the application. What's also in some of the development platforms, the Windows Web.HTTP and the IXHR platform. In these spaces, again, it is on by default. So an existing application written to these platforms will offer HTTP2 to the server automatically. And if the server happens to support it, fantastic. Then we'll negotiate it and we'll use the transport. In .NET, we are working now to try and include HTTP2 support for the Windows 10 store applications. And we're hoping that we will be able to bring this in the short term with Windows 10. We want to bring it in basically the same way, where the application doesn't have to do anything special. They just get it automatically, and they can take advantage of the protocol. And also, for applications that want to specifically use HTTP2 and some of the advantages of it, those things will be available as well. Then on the server side, HTTP2 support being built into HTTP/sys automatically. IIS gets it automatically, and ASP.NET applications will have it automatically. The exception to that is with ASP.NET, if we want to do server push from the application on the server side, they will actually have to identify the resources and write new code to indicate to the stack what they want to push. It is a change. It is not a huge change to an application, but it is a new model of delivering the content. The two places where we're not going to have HTTP2 support by default. The first one is in WinHTTP. So it is not going to be available in WinHTTP in Windows 10. It is something that we will be working on for future releases. And then the other place is in legacy web platform applications. So things that use some of our legacy platforms are not going to get HTTP2 support automatically. And this is just basically a sense of focus for us. We wanted to work on the highly hit, the main use platforms, the things like the IE and the Spartan or the windows.web.http. Also, there is another session here on the networking development platforms. And there they're going to cover specifically how to enable and use HTTP when needed. So I highly recommend that talk as well. So where do we go from here? The biggest thing is grab Win10, try out HTTP2. Your existing applications, like we've talked about, your existing sites, they should be able to take advantage of HTTP2. You can go ahead and grab the server. You can install your site on top of a Windows 10 server, and HTTP2 support will be on by default and available to any client who asks for it. You can test it and make sure that the promise of HTTP2, the better performance, works with your content. Take your applications, come and build them for the Windows 10 store, and in which case you will get HTTP2 support automatically. Again, try them out, see how they work. See how they work with other services that are advertising HTTP2 support. There are a lot that are in development now. Give us feedback. We're open. We're looking forward to having you guys use the new platform. Thank you very much.